and outputs. And flexibility can be used in three ways, where all objects are used as inputs, or some objects are used as inputs, some as outputs, or you can have that all objects are used as outputs. So example for that is our previous example of flexibility predicates for friends. So like Peter, Wine, etc. Friends are X and Y, where somebody, where X likes the same thing as Y and X is different from Y. Now, we can have that this friends is used for inputs only. So we ask whether Peter and John are friends, yes or no, true or false. And PROLOG tells true. So this is using both variables, X and Y, as inputs. Then you can select any one of them, use it as input, and ask what is the output. So now input is Peter, output is X. And PROLOG will say X is John, X is Bill from this database of facts, and false after that. You can also have X and Y where we have outputs only. X and Y are Peter, John, Peter, Bill, etc. So these are outputs only, inputs only, and mixed inputs and outputs. This is unique feature of language that is based on pattern matching. And this is why we study this, because we can have plenty of exploiting of the flexibility. And here is an example of that. If I have append, I can append list 2 and 3 to get list 1. This is appending 2 lists to get the third list. So I can also use this program in a flexible way to subtract list. So I can say, if I have list 1 minus list 2, that this is list 3, this is equivalent to say that list 1 is list 2 plus list 3, because if I have that list 3 is list 1 minus list 2, so this list 3 is 1 minus 2, then this is equivalent to saying L1 is L2 plus L3. So we say that L1 minus L2 gives L3 if I can append L2 and L3 to get L1. And so this is obvious flexibility going in opposite direction. So I can say that if I have list 1, 2, 3, 4, 5, 6, and I want to remove 1, 2 to subtract, I'm going to get list 3, 4, 5, 6. So this 1, 2 is removed from this list. Of course, you can try something that is not possible, like to remove 3, 4, 5 from the middle, and this is going to tell no, because you just remove this first part of the list. In the case list minus list, you can also say, I have this list, what can I remove and what I can get as the result? And there are multiple solutions. So you can remove empty set and then get list 1, 2, 3, 4, 5, 6. You can remove 1 from here. In that case, you get 2, 3, 4, 5, 6. Or you can remove 1, 2, or remove 1, 2, 3, or remove 1, 2, 3, 4, like here. Remove 1, 2, 3, 4, and then you get as the result 5, 6. So all these solutions are generated by this list minus list program. There is one more thing that exists in PROLOG, which is when we speak about append, there is also flatten. Flatten is the possibility to take all elements of lists, but to have them as leaves. So if I have list 1, which is 1 and then sublist 2, 3, and then list 2, which is 3 and 4 here, then if I say I'm going to make the list that has L1 and L2 inside, so list of lists, and each of them has also sublist. and create as a result L, L is going to be 1, 2, 3, 3, 4. So all elements inside. So practically, I can use this for appending this list, but it appends only leaves the tree and not the structure. And append is appending structures. So append and flatten work in different way. Sometimes you can use flatten for appending lists. That means only elements that are inside. But if you want to append the list by taking their structures inside, then you have to use append, not flatten. Now, an interesting example, how to delete an element of list. Well, if you have a list and you want to eliminate an element from it, for example, you have the list 1, 2, 3, and you want to delete 2, what you are going to get? 1, 3. So how to write the program for eliminating this element? Well, the program works like this. Decompose this in head and tail. And then if this element is the head of the list, then the result is the tail. Otherwise, you remove that from tail. So after deleting the head of list, the resulting list is the tail. Otherwise, if you cannot remove it from here, then it is in the tail. So again, we come to the same idea that we mentioned many times, and this is that you cannot reach line 2 unless you failed line 1. So the program that deletes element from a list and gives resulting list works like this. First, you decompose list into head and tail. If this element that is removed from the list is the first element, then the processed list, the resulting list, the tail. You simply eliminate this head and give as a result tail. So this is element, this is list, and this is the resulting list. Now, if this fails, what does that mean? That means that the element that we are removing is not the head, but is somewhere in the tail. Therefore, the rule number 2 is that if I have that I eliminate X from head and tail, I have to create head and tail 1 when tail 1 is obtained by deleting X from the tail. And this is the way how to delete element from the list. What we have here is the fact that when I come to the second line, I know that I failed the first one. So I know that I came here because this X is different from this head. And I can write delete X from head to tail by deleting X from the tail. So deleting X from the tail gives me tail 1, and this head and tail 1 is the result when I remove that from the tail. So it is going to go through the list, left to right, chopping heads, and when it finds to the situation where it finds this element, then it is going to eliminate it and give you the tail of that. So it is going to work like this. If you say eliminate 7 from 1 to 3, it is going to say no, you cannot eliminate because there is not inside. But if I eliminate 2 from 1 to 3, I get 1, 3. Okay? If I say delete X from list 1, 2, 3 to get list L, there are going to be 3 solutions. You are going to delete 1 and get list 2, 3, or you can delete 2 and get list 1, 3, or you can delete 3 and get sublist 1, 2. So these are 3 possible solutions. Always when you see semicolons, this is what we enter as users and ask, give me more solutions. Okay. You can also delete element X from a list that has repetitions 1 to 1. And it is going first to delete this 1, and then we'll delete 2, and then we'll delete this third one. So there are three solutions here. You have that you can delete X where X is 1, and you get 2, 1 as the result. Or you can delete 2, and you get 1, 1 as the result. Or you can delete the last one, and then you get 1, 2. So there are three solutions here. You can also delete 1 from this list, 3, 2, 1. So these are atoms, but this is symbolic atom, and this is numerical atom. So you say delete 1 from T to 1, and give me the list after I delete that. And of course, you're going to get 3 and 2. This is what I appended here yesterday, just to show you that you can have repetitions of elements, but it is nothing that is important. And here also, if I have a repetition like 2, 1, 3, 1, 4, 1, 5, 1, etc., if I want to delete 1, I delete the first one and I get 2, 1, 3, 4, etc. The remaining, what I get when I delete 1. And then after that, I delete the second one. And the library function that is doing that is called select. So I want you to remind you that there is the PROLOG reference card, which is the whole PROLOG written on a single page. I did that in 2 columns, and you have that posted on iLearn. And I hope that you printed that. It is very useful for exam and for problem solving. And you are going to find inside select function, which is practically a library function that works the same way as our del here. So removes one instance of element from list, and then if you continue, then removes the next instance, and so on and so forth. And there is also delete. Delete is deleting all instances of specific values. So if I say here not del, but say delete, then I have the library function, and it is going to delete all these ones from here. Will remain only 2, 3, 4, 5. All ones will be gone. Okay. Now again, flexibility.
Professor?
Question?
I
Yeah.
have a question.
Mm-hmm.
The 2 slides ago where you explained delete, your delete function. Yeah. Why does, when you do bracket X bar T bracket, why does it separate them? Because I thought that was a union.
This is something that we used very, very frequently. And this is the separation of head and tail of the list. So if you have this X and T, and you match this with the list 1, 2, 3, then X becomes 1 and tail becomes 2, 3. So this XT is decomposition of head and tail of a list. So when this matches XT, some list, it is going to decompose head and tail. So for example, in this case, where I have the second element that is 1, 2, 1, 3, etc. What is the head? Head is this 1. And the tail is everything from the second element to the end. Do you agree with that?
Yeah.
Okay, so that's the answer. I need to decompose head and tail. And therefore, I'm going to match this with some real values. So these are just variables. But when I come to solve the problem, I have here 2 and 1, 2, 3. I want to eliminate 2 from 1, 2, 3. So what I'm going to do is I'm going to decompose this into head 1 and tail 2, 3. And then I'm going to ask, Is this 2 equal to the head? It is not. Therefore, head 1 remains here. And then I'm going to eliminate this 2 from the tail. Tail is 2, 3. After eliminating 2, I'm going to get only 3, and 1, 3 is going to be the result. So when I eliminate X from list that has head and tail, I get the tail. If this is not the case, then I have to eliminate X from the tail. Therefore, I have to decompose the list into head and tail and delete X from the tail. And then to take this new tail T1 and append that to head. And this is the result. Okay? Now, let us use that in opposite direction. If you want to insert element in a list, how to do that? Well, you can use delete in opposite direction. I have element X that I want to insert in list L to get the list XL. How to insert that element in the list? Well, I can say this is equivalent by removing X from this list XL to get L. So X plus L equals XL. And XL minus X gives L. So I can say insert is reversed delete. And because of flexibility, I can use such solutions. So what I'm going to have is when I insert 1 in list 2, 3, 4, I'm going to get list L by inserting 1 as the first element, or second element, or third element, or last element of the list. And there should be 4 solutions. I can put 1 as the first, second, third, and fourth element in this list. Is this clear? So this is practically organized by using delete, but insert is reverse delete, which is the same as inverse function in algebra. If you have square function, inverse function is square root. So here you have that the function is delete, and this delete here. And if I use it in opposite direction, it is insert, because I'm deleting X from XL to get L. So obviously, if I append X and XL, I'm going to get this XL. So if I insert X in L, we'll get XL. And here is how this works. I can insert element in list L and say, tell me what is element, what is list. That after I insert element in list, I get 1, 2, 3. And PROLOG will say, you can have element 1 that you insert in 2, 3. That's okay. What else? You can have 2 that you insert in 1, 3. Or 3 that you insert in 1, 2. So to get 1, 2, 3, you can have 1, 2, 3, or 1, 2, 3, or 1, 2, 3 at the end. So these are 3 solutions of this insert. And select is the same, but it is library operation. So it has flexible remove one instance of element from the list. So if you have list 1, E2, E3, and you want to eliminate this E, it is going to eliminate the first of that and will create 1, 2, E3. And then you say, give me more. Then it is going to eliminate next one. So 1, E, 2, 3. And there is nothing more. Okay. You can also say, what is the list that when I eliminate this element E, gives the result 1, 2, 3. Then PROLOG will say you can have E, 1, 2, 3, because when you eliminate this E, you get 1, 2, 3. Or you can have 1 E 2 3, 1 2 E 3, or 1 2 3 E, and nothing more. No more solutions than that. So that is how the select works. Now something a little more complex, and this is the sublist of the list. So I have a list which is from here to here. So this is the list that is presented as this rectangle here. Now, I want to get some middle sublist of that list. I want to cut from here one part from the middle. Previously, we did with append just the head sublist of the list. And this is now a sublist in the middle. The idea of doing that is shown in this figure here. If I have this list, I can decompose this list into head, this part here, and this TS. What is this? We can append something anonymous to this TS to get this list L. In that case, we extract this TS. So this is what this append is doing. It is appending this anonymous part to this tail sublist TS to get L. So if I give L as the input, this is going to create for me this TS. And this TS is from here to here. Now I can say this TS is obtained by appending this SL plus an anonymous tail. And therefore, sublist of list is SL if I can cut this TS with appending an anonymous list here to list TS to get L. Therefore, this creates this TS. And then I say, I have sublist SL, the middle sublist, plus some anonymous tail sublist that gives me this TS. So the first one extract TS, and the second one extract from TS this sublist in the middle. And this is what is returned as the result. So if I go to see how this works, I can say, what is the sublist of list 1, 2, 3? It is going to be empty, or 1, or 1, 2, or 1, 2, 3. But it can be also 2, or 2, 3, or only 3. And we have also that this program repeats some solutions like this one, this empty list here, and here, and here 4 times. We can eliminate that, but the way how the program is written here, it is working in this way. Like always is programming, you can have multiple solutions of the same problem. So you can say, wait a second, I have here 3 sublists, 1, 2, and 3, and I'm interested in these 2. So why don't I put append 3 lists, list 1, list 2, and list 3, and then I return this list 2. That is perfectly possible, yes. So you can write the program called append 3. And you append list 1 plus list 2 plus list 3 to get this list L. So to do that, you append L1 and L2 to get L12, which is intermediate result. And then you append L12 and L3 to get L. So this is obvious append 3 list. Append first 2, and then append third to them, because append has 2 lists that appends. So you have to do it in 2 steps. And then you say SL is sublist of L if I can append something anonymous to this sublist, to something else anonymous to get the list L. So I'm practically cutting this sublist from the middle part of that list. And this is going to give me the sublist of this list. So I have first plus second plus third equals L, and I return this second one. So you have that first plus sublist plus third is L. Okay, so we are cutting sublist and returning that as the result. The way how this works is, again, give me sublist of this list here. It is having that sublist is empty, or 1, or 1, 2, or 1, 2, 3, or all of that. However, when you come to the end and you ask for more, it is going to continue search, because this is based on this delete at the beginning that didn't have any cut inside. So it is going to continue searching and will go out of global stack. So both system append and append one, homemade append, give the same result. And things like that happen. If you want to eliminate that, then you have to not continue with this after you create all results, but you have to stop earlier, or you have to have a cut mechanism that you use to eliminate this earlier. Now, multiple solutions. You can put all of them in a list, and this is done by the program findall. It is finding all solutions of a problem and putting them in the list. Now, this can be done in two ways, to store all solutions in the list, or to store all different solutions in the list by making a set. And set is, of course, list of elements that are all different. So if you have list of elements and all elements are different, this is a set. The set stops being set at the moment when you have that elements are the same. So these are find all and set off, and for all is testing all solutions for specific condition. Let me first introduce the situation called find all. So find all is written in this way. Find all result X from program that has A, B, and X as arguments. These are inputs and this X is output. So find all X's from this program and store them in the list X list. So if this program has solutions X1, X2, X3, X4 that you would get by manually entering semicolon. So you have some program in PROLOG that gives this solution X. And X can be X1, X2, X3, X4. So you have multiple solutions that you manually create by entering semicolon. This can be done automatically by using find all. So find all X's from program ABX and store these X's in X list. Then X list will be list that has here 1, 2, 3, 4, X1, X2, X3, 4. And then when you have this list, you can use some process program that is going to process this list. For example, to search whether you have inside something that is interesting, or to give you the number of solutions by using length, or to eliminate some solutions that you are not interested to have inside, etc., etc. So you can have find all of this find all test of AB by taking this program X from this program ABX, putting everything in X list, writing this X list, and processing this X list. So that would be the way how you can find this find all. And then you put atom A and atom B instead of AB. Of course, this is going to become much more clear in the case of example. And here is an example that shows that. So what I have here is a program that is going to give me a negative member of list L. So negative element in list L is E. E is element of list, but such that it's negative. How to give negative element from list? Obviously, you have first to extract element from the list, one member of the list. So member has element in the list and returns element. And then I have, this is library function. Element is returned from the list. And then this element must be negative. So is it clear how this works? Or there is any question about that? Negative element. So negative element is E, if E is member of the list and it is negative. So negative element from list 1, -2, 3, -4, 5, -6 is going to be negative element. And this is going to return negative element -2. I can be satisfied or not satisfied with that. If I enter semicolon, I'm going to get the next one, -4. And then the next one, -6, and there is no more than that. So there are 3 solutions of this problem, -2, -4, 6. Now I can put all of them in a single list by using findall and say negative list is a program that will be applied to this L list and create this negative list with capital N in the following way. Find all elements that satisfies negative element. So all negative elements that are returned from a negative element program here are going to be stored in negative list. So if I say, give me negative list from this list 1, -2, 3, etc., I am going to get that L is -2, -4, -6. So these 3 solutions are stored in -2, -4, -6 in a list. And now you can do whatever you want with this list here. You can ask, for example, are all of them even? And write the program that will take these negative elements and ask whether all negative elements are even or not. Or ask any other kind of question that you want to ask. Now,
Professor?
Yes, sir.
If a negative element returns more than one
No,
thing?
No, it returns always one thing and return next thing after you enter semicolon.
Okay, so
this negative element returns one value because this is member of the list. So it works like this. It first extracts one element from the list. When extracts that element, for example, this 1, it is asking, is 1 less than 0? It is not. Then, because it fails here, backtracks back to member, and then extract the second element from the list, which is this -2. And then ask whether -2 is less than 0. Yes, it is. Then it gives you this result.
So, for example, if you had, if negative element returned 2 things, would you get an error if you tried to do find all?
It cannot return 2 values because it returns only 1.
No, like if you...
Sir, it works with only one element. That means this element here can be element of any complexity. It can be a list that has 15 elements. That's fine. But it is one list.
Okay, yeah.
So it can return multiple components, but it must be a single object. Object can be complex and have components inside, but you see that find all is extracting one object from a program. So
thank you.
Here you have program that creates an object, and this object X is going to be stored in this list, but this can be list of lists or lists or whatever you want inside. So that's the answer, I think, to this question.
Yeah, Thank you.
Okay. Now, what happens if instead of find all, we put set of? It is going to work the same way, but it is going to eliminate duplicates. So if I say find all elements that are negative and put them in negative list, and give me this negative list, then if I have all negative from 1, -1, 2, -1, 3, -2, I'm going to get -1, -1, -2, -1. So this is the result. That is made by find all. Now, set of is doing exactly the same thing, but before inserting this next value, -1, is checking, is this -1 already inside? And if it is already inside, it is going to eliminate that duplicate. So if I say set of, so set of negative values, I'm going to do exactly the same as find all, but there are going to be no duplicates. So duplicates, -1, -1, and -1 will be eliminated and will be only one of them. So the result will be -1 and -2, -2 and -1. Okay? So this one is not going to be taken into account because it is member in the tail. This one is also member in the tail. And this one is not member in the tail, therefore it is going to be taken, and this one is then alone in the tail and it is taken. So practically -2 and -1 come as the result of set off. So set off is library function that is creating all solutions of program nil and putting them in negative set, provided that they are different from what is already inside. So first element is stored inside, no problem with that. But second element is checked for difference from one that is inside. And if it is different, then it is inserted. And what you get is the set of different results. Is this clear? Any question about this? The set of, which is set of all different solutions. And find all sets of all solutions, including those that are repeated. And you can have a specific number of repeated solutions. Okay. Now, if we have a program that is computing subset, if you say find all subsets of some set, you have that you are making a power set. Power set is the set of all subsets of the set. So if I have here a program that is computing subset and say find all subsets and put them in the power set, then you are going to get something like this. You can say subsets of 1, 2, 3 are 1, 2, 3, 1, 2, 1, 3, 1, 2, 3, 2, 3, and empty. So these are all, you have to have 2 to 3, which is 8 subsets, 1, 2, 3, 4, 5, 6, 7, 8. So these are all subsets that exist. And then if you want to ask, give me power set of these two elements, then you have A, B, and empty. And this is stored in this list here that has this list as elements. So you see here the situation where the result that is stored in this list is already a list. Or you have 1, 2, 3, and then you have that one element is 1, 2, 3 itself, and then 1, 2, and 1, 3. So what is stored in this list are lists. And you can have also that some of them have one single component. But whatever is the object, it is one object that is stored in the list with find all. As opposed to that, for all predicate is only for testing components. So you have that for all is telling you yes or no. It is giving you binary answer by testing whether all elements of this list are positive. So you have the list 1, 2, 3, 4. Are they all positive? Yes, they are. Are positive 1, 2, minus 3, 4? No, they are not. Okay. So you can also have whether when I compute member from this list, so 1 or 2 or 3 or 4, is this element positive? Are all of them positive? The answer is true. Okay. And here, are all of them positive? No, false. So how to do that? All positive. Very simply, you say create member of the list. So after you extract with member function this element from the list, check whether element is greater than 0. And then for all, repeat this for all solutions that can be obtained from this member function. So member function is going to check, to extract this 1. And you check 1 is greater than 0. Then for all, continue with next member, 2. Check that 2 is greater than 0. Yes, it is. Check 3, check 4. If all of them satisfy this condition, say yes, all of them are positive. If you fail, immediately stop and say no. Okay. So the result is either yes or no, true or false. Now, let us see one interesting example that is based on permutation. So I have a list A, B, C, D, E, and I want to create permuted list C, E, B, A, D. This is practically the same thing as shuffling cards in card games. So you want to do shuffling, and shuffling means make permutation of cards so that you have random beginning and you can play the game. So how to shuffle cards? You can take the first card, which is head, and put it aside. Then you shuffle the remaining cards, and you have then permuted. Then you take this card from aside and insert it randomly in that deck. And this is going to be permutation. So this is what we use in this program. And the program is first presented in graphical form. So if I have list, I have to decompose list into head and tail. Head is A, B, C, D, E is the tail. Then I'm going to permute that tail. And we get permuted tail, which is, for example, C, E, B, D. And then I'm going to insert head in permuted tail. And after that, I get permuted list. So permuted list is obtained by inserting head in permuted tail. Is this clear? What is the idea? Insert head in permuted tail to get permuted list. Now program that is doing that. So we have that if you have an empty list, permuted list is also empty list. This is the boundary condition, if the list is empty. If you have list that has head and tail, the permuted list is obtained by permuting the tail. So this tail after permutation gives me permuted tail T1. And then I insert head in this permuted tail to get permuted list P and return this P as the result. So to permute this list, insert head in permuted tail, and you will get permuted list. So that's the idea that we have here. So how many permutations will be generated? Well, n factorial, because that's how many permutations you have. So if you say permute list 1, 2, 3 to get x, you get 1, 2, 3, 2, 1, 3, 2, 3, 1, and 3, 2, 1 here, 6 of them. This is 3 factorial. You can also try to reverse that. And you can say, okay, permute this x so that you get 1, 2, 3. And again, you get 6 lists. But if you continue, it is going to enter the infinite loop. And this frequently happens. Why this happens? Well, simply because we used homemade, in this permute, we used the insert program. Insert program was program that we made based on delete. And delete doesn't have any cut in it. So it continues here search. So this is completely normal. If you want to fix that, you have to insert cut in delete, which is not relevant now, but you have that this is what works well. And then you can also use this to make a sort program that is going to be flexible. However, before that, let us see the library function permutation. So if you have permutation of 1, 2, 3, you have all these 6 permutations that are created in that way. And you can use that in opposite direction because it is flexible. You can say, give me the list so that permuted list is 1, 2, 3. So it's going to give you 1, 2, 3, 2, 1, 3, 3, 2, 1. And it is not going to enter any loop because it has some delete inside that is terminated with cut. So this PROLOG library permutation works in this way. And we can now do something that is similar to that, which is program that reverses the list. So one of permutation is reversed list. So if I have list A, B, C, D, I want to create reversed list, which is D, C, B, A. Well, in procedural programming, you know that you are going to swap A and D and swap B and C. And so you swap first and last, second and one before the last, and so on and so forth. And then after that, you get the result. However, in the case of so-called naive reverse, we can do it in this way. We can say that to reverse this list, we are going to decompose head A and tail B, C, D. Then we are going to reverse this tail BCD and create reversed tail, and then we'll append element A to reverse tail. So the situation is explained here. If I have a list that has head and tail, reversed list will be obtained by first reversing this tail. So reverse tail to get reverse tail. And then append head to this reverse tail to get the reverse list. Of course, when you have that you reverse this tail, in recursive repetition of this, the tail is going to be shorter and shorter, and eventually you're going to get empty tail. So this is the boundary condition. If you want naive reverse of empty tail, you get empty list, of course. So what is good and what is bad with this program? Ricardo, what's the question?
This is probably me not knowing enough about PROLOG, but how come it's not creating the forward list with a duplicate list that's reversed? Is it just automatically in the background know that it's a unique item and it doesn't need to have a duplicate?
No, why duplicates? You reverse list with elements that are here. And we are appending one element to elements from the list. there are no duplicates. Because if you have A, B, C, D, okay, what we are doing, we are chopping the head and appending this head to reverse tail. If you have elements that are the same, nothing new will be created. Again, there are duplicates we're going to stay inside.
Okay, that makes sense.
Okay, yeah, because we are appending a single element. Please pay attention that you cannot put here H, because append is appending two lists. So this here cannot be head, but must be list that has inside head. And then you can append reverse tail to this list. So this is a rather famous program called naive reverse, because it is not efficient. And this is very good for benchmarking. Why? Because if you have here list A, B, C, D, you chop the head, which is A, then you have tail, which is B, C, D, and then you reverse that to D, C, B, B, C, D becomes D, C, B, and then you have reversed head, reverse tail plus head, and you get this reverse list. However, to reverse this DCB, you have to chop this D. And then, so you have to reverse the list that has 4 elements, and then to reverse the list that has 3 elements, and list that has 2 elements. So it is 1 plus 2 plus 3 plus 4 plus etc. plus n. And this is O of n squared. So the good news is that this is a slow program, and you can easily adjust n so that you can measure performance of competitive PROLOG systems. And that's why this is used for benchmarking. Otherwise, if you use the reverse function, one that is in the library, you have reverse function that is called not n reverse, but just reverse, then it is flexible and it is also eliminating duplicates. So you have reverse that is reversing and eliminating duplicates. And this one is not eliminating duplicates. It is keeping list as it is. So here is an example. For example, if you want to do naive reverse of, just a second, the battery is going low. Let me give you a little bit of power here. Good. So what we have here in this example is that I want to reverse this ABCD to get R. I want to have flexible program. Well, to get flexible program, I'm going to get this CBA, but if I ask more, it is going to enter the loop. So this here is input, this here is output. And therefore, if I use it in opposite direction, sometimes it is going to create an infinite loop, in which case this is correct result, no doubt. But if I need more of it, and there is no more than that, it is not able, this program is not able to create that. And I want you to see that. So if I after that see put dot, everything is okay. You get the correct result. You also can ask, I want to reverse 1, 2, 3, 4 to get 4x to 1. What is x? Well, x is 3 after you're reversing this. Or if you want to find a reverse of ABCD, DCBA, or whatever else, all of this are just naive reverse. This here is a library reverse function. And it works in this way, so you can have full flexibility because library has cut inside that is terminating the program without entering loop that continues. So this is library reverse, and this is naive reverse that is homemade. Another thing, this library reverse is obviously the linear algorithm. So this guy here is O of n squared, this is O of n, because they have access to object, to all components, and they swap them, swap, and then after that, they create a reverse list in a linear time. So this one is fast and it is inconvenient for benchmarking. This one is quadratic and you can adjust, and so that you can comfortably measure several seconds and you can compare two competitive systems or two competitive operations. Now negation. Negation is written as not. So not of X succeeds if an attempt to satisfy this goal X fails. So I can say how to write the function not member. So that an element is not member of the set. So the idea is this: nobody is member of an empty set. So here is an anonymous element, and anonymous element is not member of this set. So whatever you have is not member in an empty set. That's the first thing. The second thing, if you have a set, head and tail, so you match this head and tail with some set. Like, for example, you have this set here, and you match with 1AV3. Well, then head is going to be 1, and AV3 will be the tail. So you are practically decomposing this list into head and tail. Now, X is not a member of this list if it is different from head and it is not in the tail. So X is not a member of head tail if it is different from head and it is not a member in the tail. You can write the program that checks whether something is a set, whether a list is a set. Well, list is a set if it is empty. Empty list is a set. There is nothing inside. If there is something inside, then what are the conditions? First, this head must not be member of the tail. So you have that head is not member in the tail. There is no duplicate. And then the tail must be a set consisting of different elements. Therefore, it is set if the head is different from tail, and then you check whether this tail is a set. By reducing recursively this size of tail, you are going to get empty tail, and this is going to be the boundary condition. So we loop through this first, second, and check whether something is a set or not. For example, if you ask, is set, for example, this one here, 1AV3, the answer will be yes. Okay, if you say, is the set 31AV3, it's going to say no, because 3 repeats here. You have 2 3s. You can also use the function isMember. So isMember X in this list? Yes, it is if X is the head of the list. If it is not head of the list, then it is member in the list if it is member of the tail. So X is either head of list, or it is member of the tail. That is member function that is defined here. Now, how to make is set? Well, you say is set an empty set, and if it has head and tail, it must be that head is not member in the tail and is set tail. So this is the same thing, but now you have here not as predicate. So if this member succeeds, not of that is failing. If this is failing, that H is not a member, not of that is succeeding. So you have that head and tail are set, contain different elements. If head is not in the tail, is not member of the tail, and the tail itself is a set, consists of all different elements. So that is the way how we used negation. Recently, SWI PROLOG started using, instead of this word not, this not plus. So plus is used to denote provable and slash as not provable. So this slash in combination with other operators denotes negation. Slash alone is not an operator. So you can have this slash plus denoting that something is not provable. Is not important at all, but if you see it, don't be afraid of that backslash plus. It is same as the word not. Word not is still approved, supported in SWI PROLOG, but it might be that in few years they are going to stop using it and use something else. At this moment, you can use not, no problem with that. So we have seen examples of flexibility and inflexibility. Flexibility is interchangeability of inputs and outputs. Inflexibility means that some inputs are strictly denoted to be inputs and some are strictly outputs. This is sometimes very useful, and I want to show you sort that is working that way. But before that, I want you to use this member function to see how member works for this list here. So if I have that E is member of list 1, 2, 3, it is going to give me first that E is 1. And we'll wait here to see what else I want to get. So element of this list is 1. I say, okay, give me more. It is going to move forward and give me -2, which is the second element. I say, give me more. It is going to give me 3. And after that, will immediately stop working, will reach the end. Because there are no more components and all components are exhausted. So member will give me 1, -2, and 3. Here we go. Now, I say I want to know whether the member, the element of the list is positive or negative. And I want to have positive elements. So I have here the program that says, give me the member of 1, 2, 3. And check whether this element is positive. What's going to happen now? It is going to create this 1, and then I say, give me more. Then it is going to try with this 2 element, but will fail with E greater than 0. Then we'll backtrack back to this member and extract 3, and we'll find that 3 is greater than 0 and will give me 3. So it is going to extract A and -2 and 3, and will succeed here with 1 and 3. And these are going to be the solutions. Now, what would be wrong, and I am showing that you avoid making such a mistake, is to say, give me positive value. That is member of this list. So we are going left to right. And this is going to create error. Arguments are not sufficiently instantiated because this E has to be instantiated, has to have value to be able to test, is it positive or not? So in this case, we first compute and instantiate E, and then check whether this E is positive. Here, we check whether E is positive before we instantiated E. So the program is failing right here because it doesn't have E. E is not instantiated, it doesn't have value. And you cannot check that whether it is 0 or not. So this is passive relationship, and E must be instantiated to be able to perform this. Okay? Any question about this? Now, I would like to show you a predicate that is intentionally not flexible. PROLOG has sort program, and sort program is sorting a list. So you have a list 7352164, and this list is sorted and gives me the result X. So if you sort that, you are going to get 1, 2, 3, 4, 5, 6, and 7. Sort, take the library, take the reference card, and you will find that sort is flexible, non-flexible, and eliminates duplicates. And there is M sort that sorts all elements. So here I don't have duplicates, and therefore I get 1, 2, 3, 4, 5, 6, 7. If I had duplicates, they would be eliminated. Now, if I do that, I can ask whether sorting 7, 3, 5, etc., I get 1, 2, 3, 4, 5, 6, 7. The answer will be yes. But if I ask, give me a list X, so that after sorting this list, I get 1, 2, 3, 4, 5, 6, 7. What am I asking now? I am asking, give me permutation of this list, of this sorted list. So give me any permutation of this. Of course, how many of them you have? You have n factorial of that. So you are not going to have sort that is flexible, because it would be a factorial algorithm. And therefore, what is inside under the hood is the fastest possible sort money can buy, and not an inefficient factorial algorithm. Therefore, intentionally, X is strictly input, and this is output. And if you try to sort X to get X so that sorted list is 1, 2, 3, 4, 5, 6, 7, the error will be arguments are not sufficiently instantiated, and you cannot do that. Now, if we want to make a flexible sort, and do that by using homemade sort. And this homemade sort will be done in this way. We are going to sort list to get sorted list. In what way? In completely idiotic way. We are going to compute permutation of list. So one of these permutation is going to be sorted list. So there are going to be n factorial such permutations. And I'm going to check, is this list sorted? So I say, I have here list 4, 3, 2, 1, and I'm going to create 4 factorial different permutation. One of them is going to be sorted, and then I'm going to return that. In order to do that, so I have here list 4, 3, 2, 1, and sorted list is going to be 1, 2, 3, 4, but in very inefficient way, as this F sort 1. So how to do that? I have to create program that is checking whether a list is sorted. So here is sorted 1, program that is checking whether the list is sorted. And it works like this. List is sorted if it has a single element. So if you have list that has one element only, it is sorted. So sorted 1 is list that has one element. If it has more elements, then I have head and second element and the rest of them. So this list here that has 2 or more elements. Ricardo, what's the question?
What is PROLOG comparing? Is it comparing the ASCII value of the characters, or does it have a type in built in?
These are not characters. These are variables. If you have characters, it is comparing ASCII values. If you have numbers, it is comparing values of numbers.
Okay, thank you.
Mm-hmm. So you have here that this is going to decompose list into first element, second element, and the rest of them. So sorted is this list. If this first element is less than or equal than second, and the remainder, that means A and B, which is from second element to the tail of list, is sorted. So this is the check whether something is sorted. It's sorted if first two elements are sorted, and then from second to the end is also sorted. And of course, by checking that, since we are removing this head and testing A, B, which is tail, this sorted one, tail, is going to become shorter and shorter as we iterate through this recursively. Eventually, it is going to be an empty list. And before that, it's going to have a single element. So if you have that all of them are sorted, and then you come to the last element, which is whatever, for example, if you come to last element, which is in this case 3, you say, yes, it is sorted because all of them are sorted before. So this F sort, if you give this list, is returning sorted list. If you don't give that, let's say sorted list is 1, 2, 3, then tell me what is the list. List is 1, 2, 3, or 2, 1, 3, or 3, 1, 2, or what 3, 2. There are 6 of them, 3 factorial. This here is the flexible sort. Library function is not flexible. You cannot put here X and give this here. I can put here X and give this here that has 7 components. But this is going to run for 7 factorial iterations. So it is extremely inefficient. And of course, we don't want to have this kind of sort. So that is the flexible sort program. So that is all what I would like to have for today. And I would like to give you a few information. So first, we have this test program, test exam that is posted on iLearn. So if you want to practice a little bit, try to work with this test. There are 2 things that you will have to read yourself. If you want to solve this test, then you have in the reader this graph problem that is here. So you have this graph problem and the problem how to go from A through F. You can go through all these traveling paths, and one of them is the shortest. We are going to study this on Monday. But if you want to have it now, read this, the solution. The solution is this one here. And you have it also posted on iLearn. That's the first thing. Second thing, you have in homework to solve the 8 queens problem. And this problem is solved in Weber's book. And you have on iLearn this chapter when you have the solution. And you also have to read that. It has 5 lines of code and nice explanation how this works. However, you should go and read that for homework from that slide that is inside the slides that are posted for Weber book. And next Wednesday, week from now, we will have the PROLOG midterm exam that will cover these things that we studied so far. Unfortunately, after that, we have only 9 meetings of this class because we have Thanksgiving break plus Veterans Day that is observed on Wednesday, and we have only 9 meetings. And in these 9 meetings, I have to cover Scheme and Ruby. So there is going to be plenty of work, and I will be a little faster than I am now. So be prepared to now focus on PROLOG, and then be prepared to work rather intensively on Scheme and Ruby that are going to come in next month and a half. Another thing is to take into account is that we might start doing a little bit of Scheme on Monday if I finish this earlier. There was also a question, how about these big examples that we have at the end of the slides? Well, here are towers of Hanoi. If you want to study that, how it works, it is this one here, solution. And then I have knapsack problem, which is very complex problem. And it has long program here. We are going to skip this. For those of you who like PROLOG and want to see how this works in all detail, you are perfectly welcome to study these solutions that I made here. And I was playing with this to make all values and optimums, etc., etc. You don't need to do that. So what I'm going to do next time, I'm going to do those examples that are important for exam. And I'm going also to go through the PROLOG reference card. And you will see that we are practically covered everything except a few things here. Some things we did not cover, for example, library functions. Since this is open notes exam, if you have that you need absolute value or random number, then you go here and find a random function and it is going to return a random integer between 0 and 10. So you have nothing to do but to use that. Or for example, is there sine and cosine? Yes, there is, okay. Or arcus tangent, for example. There is also pi as a constant and e as a constant. So you can use that if this is necessary to do something with, for example, plotting a curve or something like that. So I suggest that you print this reference card, and I very recommend one that fits on a single page. But you have this on a single page, of course, I did by making small font. So for those of you who prefer to have something with bigger font, there is one a bigger reference card over there. You can print any one that you want. And you have also these slides in the reader. So whatever you want, you can do. But the point is that PROLOG is a small language, and the whole language can fit on a single page. So that is important. On the other hand, it has solved many problems in a powerful way, and it can be interfaced with Java and with other programming languages. So you can jump from your Java program to PROLOG, solve something in PROLOG, and come back to Java and continue. So you can use PROLOG search engine if it is useful for solving some problem that you want to solve. Okay, any question?
Yes.
Cody, what can I do for you?
On homework, our homework, question 3, it talks about 2 adjacent elements. And I was wondering what the input looks like and what the output looks like.
You have that in the solved in the reader. I don't know which slide, but if you wait a little bit, I'll find it. 2 adjacent elements is solved. You were not on all lectures, is that correct? Huh?
But there's no fun if you look at the answer.
Huh? Well, I'm asking you, have you been in all lectures? Yes or no?
I missed last week.
That is correct. And this answers the question. And now I'm going to answer your question. But I have to find it first. It is somewhere here. Okay. Let me see.
It's okay.
Wait. Is this all same or 2 adjacent? So let me see, where is 2 adjacent elements? Which it is a list, element in the list. 2 adjacent, here we go. Okay? 2 adjacent element in the list. So adjacents are X and Y if they are first 2 elements in the list. So adjacents are X and Y if you have anonymous head and they are adjacent in the tail. So it works like this. You are asking what is input, what is output. You can have, because this is flexible, you can have any combination. So you can say adjacents are X and Y in the list 1, 2, 3, 4. And then what is X and Y? Can be 1, 2, but can be also 2, 3, or 3, 4. So 1, 2, 2, 3, 3, 4. You can return it in different way. You can give this as input. You say adjacent is 2 and y in the list 1, 2, 3, 4. What is y? Well, adjacent to 2 is this 3, so y is 3. So you have to write this little program and then play with it a little bit to see how it works. You can do what I did here or something else, and you can have different lists, and you can have lists inside the list, and you can put names of people inside or whatever you want. But for example, you can put here Peter, John, Mary, Kim, okay, and say is adjacent or not Kim to John, and you would say yes or no or something like that. So to practice this, this homework is for practicing these tail recursive programs, and this is tail recursive program. Okay.